Should be streaming. Oh, let's just make sure that's the case. I am. Well, it says I'm scheduled to stream, but I am streaming. Should be streaming. There we are. Am I that fucking quiet? Hello? I should be fine. Maybe.
Not quiet.
Are you watching my stream?
No, I'm listening to you through my podcast.
Yeah, well, I'm saying my stream seems a bit quiet, that's all.
I'm telling you, you aren't quiet.
Ah.
That's what I'm saying.
Ah. Oh. Alright, so we're looking at schema and programming paradigms today. Neato. So I'm just reviewing concepts in electrochemistry before I start taking a hack at the assignment. Take a look at that assignment, actually. That's the one. It's due today, but the prof gave me an extension. Oh. Georgie, what the fuck? I've already read part of this, but I'll reread it again just to make sure I'm not missing anything. Concentration polarization is appreciable when there are significant concentration gradients of the electroactive species adjacent to the electrode. We have previously discussed that concentration gradients in thin diffusion layers adjacent to an electrode surface develop. When the species that reacts on the surface must be transported at least partially by molecular diffusion. For example, in a cathodic deposition of a metal ion, the metal ion concentration drops in the diffusion film from its value in the bulk, C initial or C bulk, to its value on the surface, C surface. This concentration difference creates a concentration cell effect. The equilibrium potential of the electrode is different when the actual reduced species concentration in contact when the electrode is considered. Okay. A potential difference within the diffusion layer is set up due to this concentration effect. Using the Nernst equation for the cathodic reaction, take some metal and you reduce it to create some metal ion and reduce it to create its metal. Separately for each of the two concentration values. So the Nernst equation gives us the equilibrium potential. At these two different concentrations, where unit activity coefficients are assumed for the cation, the value E equilibrium for the cation at the bulk is the reported value for the bulk concentration. It may just be denoted as the cathodic equilibrium potential. Since the surface concentration is less than the bulk concentration, it follows that the surface potential, cathodic potential, is less than the bulk cathodic potential. The difference between these two values is defined as the concentration over potential for the cathode in this case. So the overpotential of the cathode due to the concentration, oh hi presto, is going to be the equilibrium at the surface minus the equilibrium of the cathode at the bulk, which just reduces to that if we take the Nernst equation and subtract these two. If the above equation is written for an electron transfer reaction, Z should be replaced with N, and the ratio CsC0 can be used for general notation of the electroactive species concentrations. So electron transfer. Similarly, okay, yeah, so this is just difference here is that we just have N instead of Z. Do the same thing here with the anodic. For an anodic metal dissolution, that is, the surface concentration is higher than the bulk concentration. Hello, presto. Hello, sweet kitty. Yes, you. For the electroactive species diffusing away from the electrode. Oh, hello. Are you going to chew on my microphone like you like to do, you little shit? Yes. Yes, good kitty. Oh, look at you. Look at you. Oh. Please don't sit on my keyboard, you little shit. Good kitty. For an anodic metal dissolution, that is, we have a metal at the cathode that's being oxidized into an ion. For the electroactive species diffusing away from the electrode, the overpotential at the anode is greater than 0. Physically, in this case, a limiting current can also exist. The limiting diffusion current is a consequence of the fact that the surface concentration cannot exceed the saturation limit of the ion in the electrolyte. So there's a physical limit to the rate at which the ion can diffuse away from the diffusion layer. Anode concentration overpotentials are usually very small and usually ignored. The concentration ratios can be related to the limiting current density from our treatment of limiting current density prescribed previously for the cathodic deposition of an ion. We get this shit, and then dividing the two above expressions, we get this relationship. And thus we can have the overpotential expressed in terms of currents and limiting current instead. I'm getting allergic to cats. Hey, presto. Are you making me sneeze? When the current density I approaches the limiting current density, that moves to 1, which means that the overpotential moves towards negative infinity. As the overpotentials increase sharply when the current density approaches the limiting value, the cell potential drops dramatically. It is critical to avoid operating at an electrochemical cell, or either galvanic or electrolytic, close to the limiting current density. An exception to that is when another available and desired reaction is available to consume the current, which is not close to its own limiting current. Oh my lord. Hi, presto. Considering a complete cell, the expression for the cell potential needs to be modified appropriately when concentration overpotentials are taken into account. Am I getting fucking allergic to cats? All of a sudden I'm stuffy, Jesus. Oh, you're a good kitty. You are. You're such a good kitty. Oh my god. Oh, you're so cute. Oh, hi, Moosey. Oh, good kitty. Alright. Considering a complete cell, the expression for the cell potential needs to be modified appropriately when concentration over potentials are taken into account. In using the equation below, the equilibrium potentials of cathode and anode in the cell refers to the values at the bulk species concentrations. Yes. Jesus. Or equivalently, boom, okay. Because all overpotentials subtract from the equilibrium cell potential. The concentration gradients also affect the activation overpotential through the terms of the surface and bulk concentration that modifies the exchange current density in the Tafel and Butler-Volmer equations. This effect also becomes significant when the current density approaches the limiting current. Typically, this high current density requires high overpotentials so that the Tafel equation can be modified by a factor of the concentration ratio for the electroactive species that have a developed concentration gradient. Including this factor, the Tafel equations become this. But if we're to use the current density limitation, it becomes this instead. Same thing here with the anodes. The modification of all these expressions through the term is only possible if we have information on the limiting current density of the reaction. If this term is included in the activation overpotential, it normally models effectively also the approach to the limiting current, as the current drops sharply to zero when the limiting current is approached, and for this reason the concentration overpotential is not a significant effect. And that's the example. Okay, that seems to make sense. Notes and slides. Gonna go to the last one, J. Impressed current for corrosion protection. We have previously seen some thermodynamic aspects such as Borbet diagrams and kinetic aspects such as Evans diagrams relevant to metal corrosion. One way of protecting a corroding metal to some extent is through sacrificial anodes. However, some important engineering applications such as pipelines, ship hulls, underground tanks require more advanced impressed current cathodic protection systems to be installed. For corrosion protection, an ICCP system consists of a current source, usually a rectifier providing DC current, an anode, graphitic carbons plated, platinum or iron alloys are often used, electrical wiring, and a control system installed in such a way to provide a continuous cathodic current to the protected metal. This means that the protected metal is effectively made the cathode of an electrochemical cell. The protected metal in the anode of the ICCP system must be in electrolytic contact through, for example, the ionic conductivity of soil or seawater. The main idea is shown in the figure below for the cathodic protection of an underground pipe. Are you gonna pounce on the dog? Fuck you planning. In general, Evans diagrams below shows potential versus the logarithm of current of the coupled corrosion reactions. The diagram as plotted corresponds to the case where no diffusion effects are absorbed, activation control. No, not on the fucking keyboard, you prick. Ugh. Ah, you fat bastard. Oh, Jesus. This cat just body slammed onto my keyboard for a nap. Oh, shit, I accidentally closed it. Actually, I could go to history. Tabs. Lecture notes J. There we go. All right. Oh. Am I live on here? There we go. Now I'm live. Just take a note of my stream. Okay. A continuous cathodic current to the protected metal. This means that the protected metal is effectively made the cathode of an electrochemical cell. I got cat hair in my mouth. The protected metal and the anode of the ICCP system must be in electrolytic contact. Okay. So if it is the cathode, cathodes experience reduction. And the idea is if you're let's try and understand it conceptually. My understanding as I'm getting it from here is essentially if your metal is always going to want to work towards reduction, it's not going to oxidize, which is how it corrodes. The diagram as plotted corresponds to the case where no diffusion effects are observed. The anodic reaction is metal dissolution, and the cathodic reaction can be either hydrogen evolution or oxygen reduction. Hydrogen evolution predominates in acidic and deaerated environments, while oxygen reduction is observed more in neutral and basic aerated environments. So here we have the anodic reaction. Okay. Yeah. Anode oxidation, cathode reduction. So this is essentially what it looks like when we have a metal corroding. We have the anode here, and it comes down, and then we have some sort of oxidizing reaction, which is typically the oxidation of hydrogen or oxygen. And where these two overpotentials reach, that is going to be your corrosion current and also your corrosion potential. And the idea here is we want our corrosion potential to be equal to our anodic equilibrium potential, because when the potential is at equilibrium, then no reaction is happening. In the unprotected metal, the corrosion current and potential are given by the intersection point of the anodic and cathodic curves, such that the net current is zero. In this case, I corrosion is the current density of either reaction, i.e. the corrosion current density. Supposed first that a cathodic current I applied is continuously impressed onto the metal surface by the ICCP system. This current will increase the cathodic reaction current ICAT and decrease the anodic reaction current such that the difference between these two is the applied current. So, yeah. So we apply a current, a direct current to the cathode that we want to protect. It will increase the cathodic reaction current. So, paint. What it's basically saying is we have a cathode here, or this is, I understand what's happening. This is our metal. And across the metal surface, there's two reactions happening. There's electrons going out, and this is our oxidation reaction. This is our anodic current. So this is Control Z. Why is Control Z not working? What the hell have you done, Microsoft? Has AI fucked Paint too? Did they honestly get rid of Control Z on Paint? Oh my. Control Z isn't working. That or my keyboard isn't working. Hold on. Let's open up like a text file, notepad. Buongiorno. Howdy. Okay, Control Z isn't doing anything there. I don't know if this is the right software to be checking this on, but whatever. But anyways, two reactions are happening on the same surface. There is the production reaction, where the metal is, we have our metal here, and it is going into a metal ion plus an electron. And this sees, does this see current coming into the thing or leaving it? Oh, that's right, I don't have fucking Control Z. It's got undo up here, but is undo linked? It should be linked to Control Z. Is my keyboard not working properly? Hold on, I know Krita should work properly. There we are. New file, create, GBGBU, Control Z. Control Z. Control Z isn't working on my keyboard for some fucking... Oh! What was that? Do I have to hit it twice? What the fuck? Oh. Shite. No. Don't lock the layer. Okay, now it seems to be working fine. Working here. Oh, mint. All right. And so then we have our reduction reaction, which is where we have an ion plus a metal. And that creates the regular metal. So which one is current in? Which one's current out? Either way, I guess I don't think it really matters. What the fuck was I getting at here? Okay. Yeah, when you provide current to a cathode or like to a metal, what's going to happen is you're going to increase the electrochemical potential of electrons. And so it's going to be favored to move towards the product side. because it's always a balance of, it's sort of like Le Chatelier's principle meets potential energy. Le Chatelier, there we go. Le Chatelier's principle meets potential energies. So if the potential energy here goes up, then the reaction shifts this way. So if we increase the potential of the cathode, that's what happens. Or I mean decrease the potential, because the more negative the potential is, the more active your electrons are. But essentially, in a corrosion reaction, you have this reaction taking place. The metal turns into an ion, and then you have some sort of coupled oxidation reaction. This is typically something like hydrogen. Hydrogen, 2 hydrogen atoms. Yeah, 2 hydrogen atoms reduce with 2 electrons to produce hydrogen gas. Yep. And so, this is a cathode, cathodic, cathode reduction. This is the cathodic reaction. This is the anodic reaction. Okay. Oh. All right. So something makes me think cathode should be electrons out and anode should be electrons in. That would make sense, because if you were to do this with a... Yeah, that would make sense. Anode is electrons in, because that's typically the source of electrons in a regular galvanic cell. So yeah, boom. These arrows are wrong, and you should feel bad and stupid. Yeah. So yeah, the more electrons you get into this thing, the more you lower the potential, the more you drive the cathodic reaction. Or the more you favor the cathodic reaction. Suppose that a cathodic current is continuously impressed onto the metal surface by the system. This current will increase the cathodic reaction current and decrease the anodic reaction current, such that the difference between the two is the applied current. So what happens is, we take our metal and we apply a current to it. And instead of being at E-corrosion, which is the equilibrium, not really equilibrium, but it's where the two reactions pair, we move further along down this line. And as we move down the line here, as our potential becomes more electronegative, the anodic reaction starts to move down this way, essentially. We go down this line for the anode. And so, the applied current, yeah, is going to be the difference between the cathodic and the anodic current. Thus, the externally applied current brings down the metal potential to the value of E corrosion prime, which is right here, as we were saying, where the anodic corrosion rate has been decreased, whereas the cathodic reaction rate has been increased. Yep. To completely eliminate or inhibit the corrosion current, I applied inhibition, the applied inhibition current, should be such that the electrode potential, E prime corrosion, becomes equal to the anodic equilibrium potential. The cathodic reaction at this point corresponds to point A in the figure. The overpotential for the cathodic reaction has been increased to the value of inhibition minus cathode, yeah. So basically, once we increase the current enough, the inhibition current is what is required to bring the electrode potential down to be equal to the equilibrium potential of the anode. And once we're there at that potential, the anode reaction doesn't happen because it's at equilibrium. Oh, diffusion limited current, can't forget about that because that is also important. Equal to the cathodic current. Anodic current is 0. Sweet. Oh, I have a tired puppy. Alright. Gonna leave that for another time. Diffusion limitations can significantly influence the corrosion rate and potential. The following Evans diagram indicates the most common case where the cathodic reaction displays diffusion effects at current densities lower than the corrosion current. Lower than the corrosion current. The effect is the corrosion current is reduced to I corrosion 2, corresponding to the new intersection point. And the activation controlled corrosion current would be I corrosion 1. Clearly, the maximum possible corrosion current density is the limiting cathodic current density. The cathodic reaction can be oxygen reduced or, the cathodic reaction can be oxygen reduction or hydrogen evolution. This is the cathodic, yes. What was our cathodic thing up here? Anodic. Right, we don't want the anodic reaction to happen because anode is oxidation. That's the cathodic. This is the anodic. Oh, that's a group. That's why it's being fucky. Okay. Clearly, the maximum possible corrosion current density is the limiting cathodic current density. The cathodic reaction can be oxygen reduction or hydrogen evolution. More often, oxygen reduction shows diffusion limited corrosion rate because of the low dissolved oxygen concentrations. Hydrogen evolution can also be diffusion limited, especially at elevated levels of pH. The anodic reaction can also become diffusion limited, although this is not as common. The anodic is the dissolving of the metal into ions. As a result, the diffusion limited cathodic currents, the corrosion rate, can be significantly reduced. Diffusion limitations can be more commonly caused by low concentration of oxygen dissolves in the electrolyte or low proton concentration, high pH. Unstirred quiescent electrolyte has the effect of increasing the diffusion layer thickness and thus reduce the diffusion limited current and corrosion rate. Vigorous stirring increases corrosion rates. In addition, diffusion effects will more likely feature when the activation controlled corrosion current is high. Alright. Now let's do some of the assignment. Yeah, Excel is required. No, let's create an Excel in the folder. Oh, you son of a bitch. Is this gonna be nicer? Nope. Data, no, that's not it. It's data tools. Text columns. Delimited, next with space. Hold on, cancel. Get rid. Oh, that's nice. I actually want you in here. And then delete that, delete that. There's gotta be an easier way of doing that. Oh, shite. I fucking... Why? Alright. No. There we go. Nope. Mint. Here we are. Estimate the limiting current density and the exchange current density of the cathodic transfer coefficient. All right. Insert. Nice.
I work soon.
Okay.
Are you still streaming?
Yes.
Okay.
Yo.
So take the straight section here and fit a curve to that. So that is 1.2. And then here we have 1.75. So from 1.2 to 1.75. We have mx plus b. And then we have ln est known y's. I think that should be that. It's 5, 7 here. And then this should be our x's. No, these are our y's. xy. That ain't right. Oh. Come on. Yes. Log I is supposed to be the x here, so we're going to delete that and switch these around. And then plot it. Oh, shite. Here we are. That's going to be from negative 5.44 to... this is more of a straight line. 5.44 to negative 2.78.
I work in 5 minutes.
Okay. That should be our region. Ln est. Known y's. Known x's. B is calculated normally. Do not return. Okay. Christ.